Thank you very much for joining today's iName Package Tech webinars. My name is Zurius. We are honored to welcome our guest speaker, Mr. Champin Chang from K&S, who will be presenting on the topics Chiplet Bonding, Heterogeneous Integrations. Allow me to introduce today's presenters. Mr. Jones is Executive Vice President and General Manager at K&S, and also serves as Chair of the iName Board of Directors. He is a seasoned technology industry leader with over 31 years of engineering and operational experience in the semiconductor and electronics sectors. Throughout his careers, he has held top management positions at Motorola's, Flextronics, KOA, Tenko, and Everett Charles Technologies. He holds dual bachelor's degrees in electrical engineering and computer science from the state universities of New York and Buffalo, and an MBA from the universities of Leicester in the United Kingdom. Abstract heterogeneous integrations can be achieved through side-by-side or stacked or hybrid configurations utilizing various interconnect schemes. This method encompasses both fine and coarse pitch packages, each requiring specific die bonding techniques, wafer-to-wafers, die-to-wafer thermal compressions. This topic is particularly relevant for applications that integrate multiple functionalities into a single device. Here we discuss these bonding techniques, highlighting the advantage, disadvantage, and the factors influencing the choice of method. Okay, now let me briefly introduce iName. About the iName package technical webinars, we will hold monthly basis, and next webinars will be held on October 28th. The topics and the speakers is here. About the iName, you can find more information from iName homepages, or you can contact to the iName staffs. End of the presentations, we will have Q&A sessions. So please use the question box and write your questions there. For presentation document, we will email to you with download link later. Okay, please mute your lines during the presentations. So now, shall we start? Mr. John.
Thank you for the introduction. Let me share my screen now. Just checking, is Professor Subu on the call now yet? Okay, never mind. I'll start first, okay, and then I'll let him join us when it's his part, right? The reason I invited him is because there's a lot of collaboration with us in UCLA on chiplet bonding. And I'd like him to share with us some of the data that he has worked with us in the past couple of years. Okay, so let me just get started. Okay. Hope you can all see my screen. Okay, so this is our advanced packaging overview. All right, so I'll do an introduction. I follow the agenda. We'll talk about the advanced packaging market trends, and then we talk about the hybrid market trends. So there's basically different types of technologies in bonding. We are very good in bonding, and started from wire bonding, and now we're going to advanced packaging bonding. There's flip chip bonding, mass reflow, there is thermal compression compression bonding, and there is hybrid bonding, right? So there's a few couple of trends in terms of the technology trends, and I'll explain some of that. And then we talk about the using a thermal compression bonding to do copper to copper TCB bonding, and this is also one of our key value proposition for KNS. And then we'll talk about the transition from traditional flip chip mass reflow to a thermal compression bonding. And then I'll explain a little bit of some of our packaging technology roadmap that KNS is working on. Okay, so why advanced packaging? Packaging is a new silicon. Moore's law is slowing its transistor density growth and cost reductions are slowing. So new methods such as backside power delivery, especially for the 2 nanometers, aim to improve the overall power efficiencies. And a lot of this is also driven from the AI market trends recently with larger chips and higher power usage. So there's a big push on power efficiency. And of course, as we know, that the focus of shifting from more to more is shifting towards the back-end integration. We call it heterogeneous integration in 3D structures. And these are some of the applications, like I mentioned, AI and machine learning, 5G, 6G communications, automotives. You've seen some of the cars, EV cars especially, they're full of gadgets and IoTs and edge devices in the car. And some of this are also applying to AI and some of the chiplet integrated packages. And of course, HPC or data centers and cloud computing. So let's talk about advanced packaging market trends and growth. So this is an extracted report about the trends for advanced packaging. So from Yo's report in 2025, they mentioned that the advanced packaging market value is growing to about 46 billion from 24 to 79 billion by 2030, representing a CAGR of close to 10%. And yeah, the biggest growth you can see on the right-hand side is basically the 2.5D and 3D packaging growing at a significant growth rate of about 17%. All right, overall, semiconductor is really fueled by the AI HPC growth. Mobile and consumer demand expected to contribute more heavily as the demand for AI-enabled PCs and mobile devices are increasing. And then, of course, followed by the automotive applications for self-driving and infotainment. As I mentioned, there's a big growth in 2.5D and 3D packaging towards close to 17%. And let me just kind of focus on the bottom right here, the TCB equipment, thermal compression bonding. All right, remember today's topic is about bonding. It's growing at about a CAGR to 11 to 12% between this year to 2030. And flip chip bonding, traditional flip chip bonding with mass reflow is growing about 4 to 5%. And the overall, if you average out the 3 segments of the market, including hybrid bonding, is growing at close to about 10%, 9.5%. Let's talk about the 3 major bonding technologies, right? Like I mentioned again, right, that this seminar webinar is focused on the bonding. So here we have 3 segments of the market, all right, TCB bonding, hybrid bonding, and flip chip bonding, right? Overall advanced packaging backend equipment expected to healthy growth over the next 5 years. And basically the thermal compression bonding and TCB's total TAM is actually transitioning from flip chip to TCB, and it's the highest value market, as you can see in the slide on the right. Hybrid bonding would follow on later on. You could see also bigger growth, but it's still half the size of the TCB market as it is growing. As you can see, the legends here with the TCB having the biggest bar, followed by a flip chip, and then as you can see, hybrid bonding it's growing nicely. TCB, but you can see that based on the market size, market 10, the thermal compression bonding is the largest in the next 5 years from the applications space that we just talked about, like AI, HPC, automotive, and AI, PC computing, and so forth. And this source also came from the 2025 Yo report. Okay, so let's talk about the transition of technologies from flip chip to TCB. Thermal compression bonding and flip chip bonding are both very critical to the die attach technology semiconductor packaging. All right. Flip chip, while still indispensable for many mainstream applications and on cost sensitive, it's a very mature technology. It's also plateauing. However, the TCB right now is riding on the AI HPC, high performance computing market segment. All right, and this shows the difference between a flip chip technology versus a thermal compression. And one of this driven is number one is the pitch, okay, and the second thing is wall pitch, right? As you can see, as you're going through a mass free flow or multiple mass free flow steps, heat will become an issue. You have a substrate wall pitch, you have die wall pitch, and then you have a chip gap variations from the different chip sizes, chip packages. As they're being put together, you can see, die tilts, wall pitch, okay, all becomes a concern, especially when you're driving down to a finer pitch as the intensity increases here, right? Right, this is just a typical flow of the flip chip attach process using the mass reflow, solder reflow. All right, so here we're very focused on the solder process. This is a way also of attaching the die, all right, to the substrate. But as like I said, you're introducing heat at the different stages of the package integration, and as more heat is being introduced, the challenges becomes higher. So let's talk about thermal compression bonding. All right, thermal compression bonding is outpacing flip chip bonding. So we are also introducing in heat, but this is called local because the heat is introduced at the bond head level. And TCB satisfy technical requirements of AI accelerators, high bandwidth, memory integration, chiplet-based designs that are driving the semiconductor latest generation of products. And TCB's growth is catalyzed by the explosive demand in AI HPC. And these sectors are seeing multiple fold increases investments and unit shipments. And that is the reason why there's a lot of investments, advanced packaging capacity, across the world, right? From Asia to US, Europe, and so forth. Market research also showing that the TCB is actually growing about 2 to 3 times faster than conventional flip chip equipment as a result of these requirements of AI HPC. So the major equipment suppliers, KNS, BESI, and ASMPT, they all have ramped up our TCB development and leading semiconductor firms like TSMC, Intel, Samsung, ASE, Amkor. This is just a couple, and they are all adopting this thermal compression bonding as the requirements for AI and HPCs is starting to grow. Okay, so then we talk about the next phase of hybrid bonding. All right, hybrid bonding and thermal compression represent 2 generations of advanced die attach technologies. Hybrid bonding achieves bumpless. Okay, so there's no bumps. It's direct copper to copper at sub 10 micron pitches. But again, some of this could have been challenges if TCB continues to get smaller pitches, and hybrid bonding could be focusing on even finer pitches like sub 5 microns. So this enables ultra high interconnect density for 3D integrated chips. TCB typically uses solder, okay, or copper microbumps with heat and pressure. So the key thing here is heat and pressure, right? Reliably bonding dies at fine pitch. Today the market is around 20 to 40 microns pitch with high yields, while hybrid bonding is viewed as a longer-term solution for higher density and even finer pitch for heterogeneous integration. But there are also other challenges with hybrid bonding, which I will explain a little later. Hybrid bonding tools have also a smaller market right now, but it's growing very fast to about from 152 million, growing at close to a 20% CAGR rate. TCB, thermal compression bonding, is the workhorse of the current generation, and advances in TCB technology such as fluxless bonding and even direct copper-to-copper bonding is now suggesting pitch capability down to 10 micron, and thus potentially extending TCB applications typically reserved for hybrid bond. Right. So we would discuss some of this in the subsequent slides between the difference between the hybrid bonding versus thermal compression bonding, because thermal compression bonding is the workhorse right now for most of the devices at 20 to 40 microns. As the pitch gets down to sub 10 microns, and then there'll be a flavor of mix between TCB versus hybrid bonding, depending on the package type and package density and package height, and a lot of different applications. Okay, hybrid bonding. All right, hybrid bonding is it's a higher interconnect density, allows interconnections under 10 microns, improving speed and reduce latencies. It's got a better electrical performance since now we are eliminating the solder, so it's a direct copper bond and lowers the resistance and power use, and also speeding up the data transfer. Right, so speed, power, and also lower resistance. It improves the overall thermal management, eliminating bulky materials, and enhances the heat dissipation for higher power uses. Power usages. It's a true 3D integration and enables real 3D stacking, saving space and improving performance. Right, as you know, package is getting thinner, dies are getting thinner, package are getting stacking up more. So scalability is very key. That's why it supports various chip types and processes, ideal for modular chiplet designs. So here is basically a process flow extracted from a presentation here from Yo, all right, plus report. Okay, it's basically the expiry of HBI flow. Basically, the top shows a die to wafer bonding, and it shows basically preparing a base of a metal and then a CMP polish, a dice wafer, a dice activation. It could be a plasma activation, and then you have the wafer prep, you have the CMP, you have the clean, and then you have the wafer surface prep, and then here you have basically the bonding, right? Flip, align, and bond. So this is basically you could do with either wafer to wafer bonding or die to wafer bonding. All right. Some of the challenges, like here I mentioned earlier, surface defects and cleanliness is important. So here you're basically interacting between two copper surfaces, copper to copper. Surface defects have to be absolutely clean. All right. Contaminants such as particles and residual cause bonding voids, reducing quality, and especially the die to wafer process. And then, of course, the copper pad recess, and you recess the copper pads after processing with harm bonding and performance. Improve the CMP dielectrics are also being developed. And of course, you can see this flow here. The cost and complexity of this flow with clean steps, activation steps, CMP steps, and quite a lot more steps added besides the traditional flip chip or TCB bonding adds costs and complexities to the hybrid bond steps. And typically, as you see that the hybrid bonding is very much integrated with the fab foundry process, because as the wafers are coming in from the fab or foundries integrated with the advanced packaging, the HBI, the hybrid bonding, works better in a foundry where they have the fab wafer process together with advanced packaging, because you can start to adjust and tune the process from upstream in the wafer to your 3D stacking process, right? Whereas in the OSAT environment, where you're taking in different die sources or dielets or chiplets from different sources, there's a lot of unknowns because you don't have the control of the upstream process of the wafer. So of course things are getting better, improving, but there's still a lot of integration challenges that the OSATs or back-end advanced packaging facilities will need to deal with incoming dielets or chiplets coming from different sources, especially when you're putting a package called heterogeneous integration with multiple chip packages in a single package when you do die to wafer bonding. All right, this is just a picture from one of the AMD slides in some of the conferences. Okay, so market trends. So Yo has projected that hybrid bonding equipment will grow at a big rate of 21% CAGR from 25 to 30, as you can see here. On the right, the total bond module demand expected to be at least 150 per year, but you could see a significant upside if the adoption of silicon photonics or sensors And of course, the equipment set differentiation will be driven by device pitch scaling from 9 to 1 microns, right? And you can see here basically another slide that we show in terms of the TAM interconnect from Yos, showing the total market, broken down by 9 micron pitch, 3 to 6 micron pitch, and 1 micron pitch, right? Okay, of course, 1 micron pitch will take a little longer going from low volume manufacturing to high volume manufacturing, but the mainstream will be around the sub 10 microns. And like I mentioned, the 1 micron will take a little longer or later for adoption to take off. Okay, then we move back to the TCB fluxless capability. All right, so K&S has developed a fluxless in situ formic acid thermal compression bonding. And we have over 200 advanced packaging tools delivered with over 50 equipments with formic acid fluxless capability in high volume manufacturing. Formic acid fluxless capability is fully developed in-house by K&S and only mass production fluxless TCB to date in production globally. And the major advantage over alternative technologies is an in situ oxide removal. It removes risk of reoxidation. So this is in situ, that means as a bond, it basically introduces formic acid. So you're actually cleaning and bonding at the same time to reduce the risk of reoxidation especially on the copper surface, right? And of course, there's no damage to the sensitive device. It's a chemical process, so it cleans. Formic acid has been around in the industry for many, many years. It's a known process of clean, and basically we are introducing this as an in situ formic acid TCB flow. So it creates a wide process window, as we can see that quite a lot of equipments are in high volume manufacturing production. So we have done it over the last couple of years working with different customers, and this is basically a proven technology in production. And then the other technology that K&S has, and also the market is also introducing, is the plasma capability. It's in qual stage to meet customer interest in providing flexibility. It's a faster time to market as commercial systems are available. As you can see, a picture of plasma modules, and K&S basically has expertise to basically integrate the plasma modules into the TCB bonder. And we can also supplement the process of plasma as well as the formic acid, and I'll explain that in the next slide later on. All right, so of course, every integration has challenges. Introducing the technology, we are continuing to address technology concerns. But this is in production, and this is in different stages of qual, and we believe that at a very quick time, the process of qualification of plasma and formic acid in production will be coming up very shortly. Okay, so when we introduce formic acid, we believe we have a wide process window. And when we introduce the hydrogen-based plasma, effectively removes some of the tin oxide surface on the tin surface. With the addition of both formic acid vapor and plasma, it clears the top layer, okay, letting the formic acid remove a deeper oxide. Formic acid vapor overcomes some of the plasma directional limits or cleaning hard to reach areas. So that's why we believe that two could be complementary. So combining both, okay, plasma scans and shorter formic acid exposure gives you a very nice clean bond. And this sequence also reduces the byproducts of formic, tin formic byproducts, and prevents also voids in the solder. So here it basically shows a formic acid exposure on a formic acid process on an 11-second formic acid exposure. And we measure basically the bond force or the after the melt. Okay, this is about negative 2.1. So the lower it is better. All right, so the plasma only process here, you have a 3.1 second plasma exposure on both the source as well as the target wafer. And here is about a 0.2 newtons. And if you kind of look at basically the combination of both plasma and formic acid process, it reduces from 11 seconds or 3.1 seconds to a 1.1 for plasma exposure and a 2-second formic acid for both source and target, basically creating close to about a 3.1 second total exposure time for both plasma and formic acid, and also create a good force after melt at 2.2 newtons, right? So this is some of the experiments that we are doing, that we have seen the complementary effect of plasma and formic acid in the fluxus bonding process. All right, so let's talk about the KNS technology roadmap. Right.
Chanpin, just to let you know, Professor Iyer is online now. Okay.
Oh, thank you. Okay, I was trying to text him while talking. All right, so you got him. Thank you. All right, Subu, thanks for joining.
No, I was unable to get my mic to work when you were trying to introduce me, but that's okay. Everything's good.
Okay, good. Thank you. All right, a couple more slides and it'll be your turn. All right, so KNS technology roadmap, large format. All right, okay. You can go to YouTube, you can go to Google, you can go to all kinds of co-pilots, and you can be able to see CoWoS capability scaling. All right, okay, large chiplets surrounded by memory HBM memory dies, and you can see these modules are getting bigger. All right, so KNS is basically aligning our roadmaps to CoWoS, EMIB scalability to large format. Right, so large format could be large die, large substrates, so going up to about 150 millimeters interposer packages on substrates, and this is basically to meet the bonding needs for both RDL panels and as well as quarter panels. So 310 by 310 looks like the most eminent one coming up soon, and of course going even bigger sizes as the scalability of the roadmap increases for AI and HPC computing. And so we are following the roadmap, we are following the trends, okay, for both the CoWoS and EMIB scalability. We are addressing our equipment roadmap towards the CoWoS and EMIB scalability for large format, for both die sizes as well as substrate sizes, and we will continue to go towards that trend as everything gets bigger and bigger, as we know that the wafer, when you put a large die in the wafer, it's going to be less efficient. So people are moving towards a panel. And I think the first step to start the panel will be a quarter size panel, followed by the larger panel later on in the later years. But KNS is focused on addressing those roadmaps in both the CoWoS and the EMIB scalability. Okay, let's talk a quick few slides on copper, and then later I'll introduce Professor Subu. So this is an alternative to hybrid bonding, and I mentioned a lot about the 10-micron node where people are adopting to hybrid, but KNS has also developed a capability using now fluxless copper-to-copper TCB. All right, so it's the same equipment set, formic acid delivery hardware used for solder can be extended to solderless copper-to-copper. So discussions will be copper-to-copper TCB surface prep, copper-to-copper process options and examples. And then, of course, we have cost comparisons with hybrid bonding. It's a much more competitive solutions, and you can continue to push the scalability of the node down to sub 10 microns. And Professor Subu will talk about some of that. And of course, we also have a thermal conductivity comparison of hybrid bonding to a copper-to-copper TCB. So the prep, all right, so CMP, all right, so here basically you have a chip pillar, 1 to 100 nanometer range, copper oxide layers. You basically apply a force and a heat to create a flat surface and initiate a diffusion. So the way it bonds is basically diffusion, right, with temperature and a force, right? So this is about a 50 megapascals, okay? And you can see the deformations and the copper oxide reduction. And of course, when you do a CMP planarization, it creates a much more flatter surface. The bonding pressure is lesser here. It's a 10 megapascal compared to as plated versus a fly cut. So the CMP process is recommended in this process of getting towards a flatter surface, and then you can apply heat and force where the diffusion happens between the two copper surfaces. We have done a couple of different approaches to this, and Professor Subu will talk about how we do the copper pillar with the ALD passivation. You can see a little bit of protrusion here. All right, here we have a pre-applied underfill organic. All right, and this is in collaboration with Resonate. And we have a tool in the US joint facility working on these collaborations on the pre-applied underfill organic materials. And then we also have a customers in Asia, okay, using an inorganic dielectric bonding. You can see, you know, the whole process between the ALD passivations with the pre-applied organic underfill versus the inorganic dielectric. And here where when the cooling happens, you can see where the diffusion of the copper-to-copper interface happens, right? This one has a underfill material. This is basically an ALD passivation. And this is in collaboration with UCLA. We have our tools in UCLA working closely with Professor Subu and his team. We've got great work, great results, you know, results coming up. And we have been presenting this in ECTC conferences, as well as the IMAP conference actually happening today in San Diego. All right, so this is the pre-apply. I will explain a little bit about this pre-apply underfill. This is in basically the Resonate process. It's a spin-coated application process. It's a bump wafer. You apply a resin and partially cure it. You CMP process, and then you dice it. And so the die size here is about a 5 millimeter, 20 micron pitch, copper pillar height about 5 micron, and then we have a 0.5 nanometer CMP after finish, and we apply an underfill thickness of about 4 microns, and then we do a little bit of a protrusion of a 30 nanometers, and then we anneal for about 2 hours at 250 after bonding. So this is one of the method which I mentioned. This is method number 2, all right, here. And this is what we've done. And here you can see that after the new process, Pelias shows grain growth, okay? And the wavy surface is a good confirmation of the good joint between the two surfaces of copper. And there's no signs of any recent degradation after the annealing. All right, so this experiment works quite well, and we'll continue to do more DOE's experiments on getting a better process window on that. Okay, so in summary, I like to mention that the AI growth, advanced packaging is really experiencing rapid expansion propelled by AI, HPC, 5G, 6G, automotive, IoT, growing approximately about 10% and reaching about the 79 billion by 2030. Bonding technologies, thermal compression bonding is surpassing flip chip bonding and adoption, all right, due to the compatibility with the applications of AI, HPC, and chiplets architectures. While hybrid bonding provides high density, but involves much more greater complexity, like I mentioned. And today it's a much smaller market, much more, I would say, a little more niche, but it is growing, especially as the node smaller pitch. KNS solutions, KNS TCB supports the submicron pitch processes, demonstrating maturity for the tin and copper bonding in high volume scenarios. All right, and then we are also in mass production on the fluxus process in different sites globally, utilizing the formic acid process. This is a big enabler to the robust packaging solutions for larger die sizes exceeding the full radical sizes, like I show you the roadmap for both the CoWoS and EMIB growing. And today the pitches are about less than 20 microns, and we believe we can scale down even sub 10 microns with the TCB fluxus formic acid process. All right, KNS is advancing direct copper-to-copper TCB technology for solderless interconnects and targeting ultra-fine pitch applications below 10 micron as a low-cost solution for 3D stacking applications. As you know, that as we continue to push the roadmap of TCB and further down to 10 microns and below, the cost of ownership will be most attractive for OSATs, for foundries, as they can reuse the current tool sets they have on TCB. They can incorporate the fluxus capability, extend the process window, extend the node capability down to 10 microns. And this is a big, I would say, enabler or competitive advantage for the TCB. Today, it's still the mainstream for some of this, we call the advanced node bonding. And we believe that with the technologies of both flux type and fluxus type and TCB, KNS has a good solution to scale continuously down to 10 microns. And this nicely leads to Professor Subu's introduction of thermal compression for chiplet-based systems. I hand the time over to you, Professor Subbu, and thank you for good years of cooperation working with you at UCA Labs, and we look forward for even more collaboration as we continue to scale our TCB to finer nodes.
Yeah, so thank you, Champion. Yeah, and I'll tell you to advance the slides because I think you're still controlling the slides, right?
Correct.
So let's go to the next chart. So first of all, we are very grateful for this very, very long-term, sustained, and deep collaboration with KNS. I mean, and I think we benefited a lot, and I believe the industry too will benefit tremendously from this collaboration. So as Champion has mentioned, TCB is the workhorse for chiplet dielet assembly today. And today, TCB represents the largest incumbent base of advanced packaging assembly today. All CoWoS, all 3D stacked memory, HBM, HMC, all EMIB, all employ solder-based thermal compression bonding almost exclusively and yields well, I mean, in high volume manufacturing down to 36 micron bond pitch for both interposers and 3D stacking. Now, extending TCB to finer pitches requires the elimination of solder to avoid the complete intermetallic formation and the problem of solder extrusion, which leads to shorting and other reliability issues when you kind of try to make the pitch shorter. So the key thing here is to see how can we eliminate solder and do copper-to-copper bonding. And we have been working, as I said, with KNS to develop a reliable high throughput and copper-to-copper TCB process. And we started with what is called and we're going to the Aptura platform, which is their latest technology, right? We started with the Apama platform, and now we're moving over to the Aptura platform, which you can see in the background there. And we just took delivery of an Aptura machine, which will actually be fantastic. And we also do this as a service for an application service for people who are interested in making copper-to-copper TCB. Next chart, please. Yeah. So yes, why don't we just skip the animations? Otherwise, we'll be go back. Okay. Yeah. So the problems of fine pitch solder, right? I mean, so bridging and brittle intermetallic. So what happens, right? Is as so the argument is, okay, suppose I sort of reduce the amount of solder, then I won't have these extrusions, which are shown like in the left-hand picture micrograph there. And so the question is, okay, so we'll start reducing the amount. But what happens when you reduce the amount is all the solder gets converted to intermetallic. This intermetallic is extremely brittle, and it reaches the point where the bonds are not very reliable, right? So the whole idea now is saying, okay, how do we kind of eliminate solder completely? And as Chanpan has mentioned, high planarity of surfaces with low roughness and pristine mating surfaces, such as, and we get those pristine surfaces either through argon plasma treatment to remove surface contamination, or more recently with hydrogen plasma treatment to reduce surface contamination. And so but the point to make here is that the surface is prone to oxidation and needs some sort of an inert or reducing environment. So basically, as you apply pressure, these surface asperities are reduced. Let's go to the next chart. Yeah, so we've done a lot of very, very systematic studies on understanding the effect of pressure and temperature. And basically, the principle is actually very simple, right? When you apply pressure to a rough surface of metal, right, you flatten that surface at the atomic level. And when you apply pressure and temperature, okay, and apply, as shown here, you're able to actually achieve very, very good surfaces. And you can make these surfaces over the area of the dielet, right, which I show on top, to be reasonably good, so that any protruding surface asperities, okay, get flattened completely. So, and then of course, we have temperature-induced grain growth across the bond line, and this ensures good bond. And this work was done both on gold surfaces as well as copper surfaces. Gold actually will bond at a slightly lower temperature because gold is softer material compared to copper, and that actually helps a little bit. And so for most of the 3,5 materials, right, that we do, we actually thermal compression with gold, but for the silicon-based materials, we actually do it with copper. Next chart. Yeah. So now, how do we do this? So, so one of the big issues is in thermal compression bonding, right, is that the throughput is something to be concerned, okay, about, and that is because as you do each die has to be cleaned in situ and placed in situ and so on and so forth, and aligned. The alignment process actually does take a long time, and the alignment process actually is done at relatively high temperatures, right, 120 degrees Celsius. And this actually is the Achilles heel of thermal compression bonding. We need to figure out how to align at lower temperatures so we can get better overlay tolerance. So what we've been developing at UCLA using the APAMA sort of platform is what is a two-step process, which separates the placement process and the grain growth process. And if we, in step one, the dielet placement, okay, includes the alignment, the cleaning, and the tacking. And that is done at a lower temperature than the temperature at which we would tack the surface. Okay, so we do that around 120 degrees Celsius. And if we just go to the next chart, yeah, so here is where we actually introduce the formic acid. Okay, the formic acid will then reduce the surface oxide completely, and then we do an alignment step, okay, which is a second order alignment, okay, and then we actually bring the die down and quickly heat it up to about 250 Celsius and apply a bonding pressure of about 50 megapascals. So I use bonding pressure, right, rather than force, because at the end of the day, it is the pressure on the individual pillars that actually is important, okay? And so the force that you have to apply, okay, has to be integrated over the number of, on the pillar area, okay? And that is very important. So when we started, right, we were doing this all in one step, and our throughput was about 90 units per hour. And then we kind of went to this two-step process in the APAMA tool, and we were able to get about 320 units per hour. And when we go to the Aptura tool with the two heads and so on and so forth, we should be able to easily get to about greater than 1,000 units per hour. At about 1,000 units per hour, right, this becomes a very, very attractive process, okay, for thermal compression bonding. Now, the beauty of thermal compression bonding, of course, lies in the fact that it doesn't require the incredible process tolerance, say, that hybrid bonding has, right? And since there's a tremendous installed base of thermal compression bonders, okay, if we are able to actually, with process and enhancements to the process, make this possible to get to very fine pitch, okay, then this is the preferred technology actually for many of the advanced packaging constructs that we are talking about. So once you do the stacking, the last step is actually an annealing. And this annealing actually is done in a furnace, okay, or it can be done in a single wafer tool as well. And basically, we heat it up to around 350 to 400 degrees, depending on what kind of process we're using. And we are able to get a mil-spec bond, both from shear and pull tests, okay? So I think this process, in our opinion, is actually a very, very robust process. And we've been able to get routinely, okay, 10 micron pitch using the APAMA tool, which is our last generation tool. With the new Aptura tool, we're expecting to be able to go all the way down to 5 microns, okay, with careful work. I mean, and I think today the best we've demonstrated, okay, is actually an 8 micron pitch thermal compression bonding copper to copper. So let's go to the next chart. Yeah, so what is the bonding mechanisms? Jumping can just go all the way, yeah. Okay, and so what happens is when you bring this thing down, right, and you make contact, wherever you make contact, with temperature, right, you create a diffusion controlled mass transport. Okay, and so when you apply pressure and temperature, there's also grain boundary growth. And because if you have and wherever there is no contact, right, there'll be a void. Now this void, by the way, this process is very, very similar to what happens in hybrid bonding as well, except the method in which we apply force in TCB is an externally impressed force, while in the case of hybrid bonding, it is thermally induced force caused by the expansion of copper. But the fundamental mechanisms are very much the same. So basically, you end up with these voids, and these voids then have to disappear, and they are disappeared by further diffusion. Okay, and you can get rid of most of these voids. Now, depending on the microstructure of the material, right? If one material has, say, a higher diffusivity than the other material, or there are more grains in one because of differences in texture and so on, the dynamics of the void formation and the void migration will actually differ, as shown in the right-hand side. So you could actually get to the point where these voids are very, very far away from the interface, and there is no fundamental issue anymore. By the way, if you do this with hybrid bonding, you will see very much the same effect, because at the microscopic level, these two are the same. The big difference, okay, between hybrid and TCB lies in the fact that we are only controlling one thing in TCB, while we have to do two things at the same time in hybrid bonding. We have to do a copper a dielectric bond, and then we have to then follow it up with a TCB that is thermally induced, okay, by expansion of the copper by heating it to high temperatures. So now, the beauty of this is that the way we do this is we let the pillar protrude slightly, and by slightly, it doesn't have to be a lot. Even a few thousand angstroms of protrusion are adequate. I mean, it's whatever you can actually achieve reliably on the surface, right? And again, remember that our focus here is on die to silicon substrate bonding, which is going to be the most important type of assembly going forward. So we've actually done lots and lots of reliability studies on this, the temperature, humidity, and so on and so forth, and we don't see any fundamental problem in the reliability of these thermal compression bonds. And we have done this with commercial chips. We get these chips from TSMC, we get these chips from global foundries, and so on and so forth. And there is no issue at all. We're able to get all these different foundries to work pretty much the same way with the same process. Okay, so there's no like customization of the surface and things of that sort that we hear about in hybrid bonding. I mean, we can do vanilla dyes from anybody and bond them. Next chart. Yeah. So this is an example of some of our current sort of things. We have two processes. Okay, one is called a low temp anneal, and the other is a high temp anneal. And obviously, we like the high temp anneal, but there are many cases where the low temp anneal is the one that we have to use because of various other constraints. And so today, right, the die cleaning time, okay, is about 3 seconds. The die placement time, which is a big component, is about 5 seconds, okay? And then we have the chuck temperature, which is the substrate temperature, which is held at 150, 120 degrees. And the die temperature is also the same temperature while we do the alignment. And then there's a tacking pressure of about 50 megapascals, okay, and a annealing temperature of about 300 in the low temp case and 400 in the high temp case. And the annealing pressure during this last process, which is all the dies are now being tacked, right? So we're annealing all of them together right now, is about 100 megapascals or 50 megapascals. Okay, and that is done by putting a weight basically on the die. And you can see here in these cross sections, right? The bond line. The bond line is actually where the dashed line is. Okay, and what you're seeing there is in this case a 3 micron pillar that is jutting out slightly above the surface, and that bonds to the pad which is on the top. And you can see the beautiful grain growth There's absolutely very little remnants of voids. I mean, if you look very, very carefully, there'll be one or two voids, but they're far away from the interface. And this is a typical sort of cross-section that we get. I mean, so, if you send us a wafer, we'll bond it for you, and you will get pretty much the same results. Okay, next chart. Yeah, and so using this approach, right, we've been able to actually successfully demonstrate assemblies on our platform, which we call the silicon interconnect fabric. The silicon interconnect fabric is just a silicon wafer with multiple wiring levels on top, terminated with these copper pillars that I showed you before. And we actually place these dies actually very, very close to each other. On the left, we have about 460 heterogeneous dies actually that are attached to the substrate. On the right is actually a functional sort of assembly, which consists of each little tile there that you see is actually 8 dielets. And those 8 dielets consist of 4 processor dielets, which are based on the ARM architecture, and then an SRAM, which is all of which were fabricated by TSMC. Okay, and so we attach these using this process that I just described, and allow us to actually produce these large assemblies. Okay, and the gap between the tiles, each tile has 8 dielets, right, is really so that we can actually probe and make sure that that 8 tile is functional. Okay, so I think this is a very strong sort of demonstration of this. So we've been able to do dies, both silicon dies and 3-5 dies. Like the 3-5 dies are mainly for RF applications as well as for power delivery applications with gallium nitride. 60 micron interdielet spacing. We can go as low as 20 microns interdielet spacing, and with an alignment accuracy of about 1 micron. So, today, right, 10 microns we can do quite well, and we've demonstrated 8 microns, and with the new tool we expect to be able to go to about 5 micron pitch. And next chart, please. Yeah, and this is go back. Yeah, and this is another application where we connected 4 TSMC dies. Okay, this is 16FF dies, and also GlobalFoundries 22FDX dies the same way, again, functional. And we actually presented this back in 2021. And this was the first functional demonstration of 10 micron pitch. I mean, before anybody had done it, and we did it with TCB. And what I really want to emphasize here is, at the university, we don't have a very fancy clean room, right? It's a university clean room. And we are able to actually prepare these surfaces and bond these surfaces with the previous generation APAMA tool and get these kind of results. And what I want to impress upon you is how robust this process is, how robust and how well we can actually do this even in an environment such as ours. Okay, so if you were in a real fab or a real OSAT with clean areas and all that, I think it'll be a lot more easy to actually pull this off, and I'm confident that will happen. Next chart. Yeah, so now, of course, there's one more question that needs to be answered, right? And this is a very important question. First of all, right, there is a gap, okay, between the die and the substrate. And this gap is typically of the order of several hundred to a few thousand angstroms, okay? And so the question now is, do you have to passivate this gap? You don't need to put underfill here because the bond that we have, the copper-to-copper bond, is stronger than any underfill that is available, okay? However, because of misalignment, right, you will have areas where the copper is exposed. And when that copper is exposed, right, it can oxidize, and that can lead to all kinds of reliability problems. So how do you solve this problem? We obviously, the gap is too small to be able to inject anything in between. However, so what we do actually is we use ALD aluminum oxide, okay, and just about 10 nanometers or so of aluminum oxide, okay, it can penetrate. I mean, and we've been told that we can actually penetrate very long distances with ALD. We haven't done that. We've gone all the way, but we have been able to get fairly good coverage for reasonable sized dies. Okay, in this process. Once we do that, okay, we are able to get excellent sort of reliability. We've done humidity studies, mil-spec humidity studies, like all the way to 85 degrees Celsius with 85% humidity, back and forth, cycling all the way from liquid nitrogen temperature all the way up to like 150 degrees temperature, back and forth many, many times. And everything looks really, really solid, okay? And so this AL203 passivation approach actually is very good. Now, people will sometimes say, oh, you don't have these surfaces in intimate contact, so there's going to be a thermal issue. That is not true. Okay, we have done good, solid calculations and show that the total thermal sort of penalty that we pay for a 1 watt per square millimeter die, which is a fairly large amount, right, is less than, I would say, 1 degree. Okay, so there is no, because even if you bring the oxides in contact with each other, they are not going to conduct too much of heat. All right. Next chart. Yeah, so let me quickly summarize. I think metal-to-metal solderless thermal compression bonding is a very versatile technique for scaling bonding pitches, and I believe we can go down to 5 microns. I think I expect to be able to show this with my students within the next year or so. With our collaboration with KNS, we have been focusing on multiple aspects, understanding and developing reliable thermal compression bonding processes, better cleaning processes, including atmospheric hydrogen plasma treatment to improve the quality, throughput, and reliability. And then we have been applying these processes for active and functional die assemblies. So we've also done sort of other kinds of bonding, such as copper to gold and copper to aluminum, etc. And those have different levels of success. I think increasing the throughput for high volume manufacturing is one of our key sort of goals here, because we want to be able to get to the point where this is a very viable sort of manufacturing process, and we're very, very close to actually doing that. And then the most important thing I would want to leave you with is we want to extend the legacy of the TCB installed base from about 40 microns, which is where it is now with solder-based TCB, down to sub-5 micron bond pitch. And I think that should be my last chart, John Ping, if you want to just,
Okay, thank you, Professor Subu. So Grace and Masahiro-san, you want to take over the session on Q&A?
Yeah, great. Thank you both very much. Very interesting presentations, and great to see the progress that has been made and the speed at which that progress has been made to drive us down to the higher density feature requirements. We've got a couple of questions. If we don't have time to answer them, we will share them with Subu and Chanpin and get answers for you directly. But let me just address some of them because I know we're running out of time. So one of the last ones that came in was any information on the copper to copper thermal compression cost and thermal conductivity comparison versus hybrid bonding.
Chanpin, you want to take the cost, and I'll take the other question, the thermal.
Yeah, so we actually did a modeling, okay? Okay, so there's two costs in any factory or any fab, right? One is CapEx and one is OpEx, okay? So CapEx is basically the number of equipments you need to purchase to form the line. Right, as you know, and I show you the whole process of the hybrid bonding basically includes CMP, cleaning, activation, hydration, everything, right? So the whole process of CapEx is significantly higher, all right? So I have heard from customers that quote up to 10x, okay, in terms of CapEx, all right? So, but again, it varies depending on the process, depending on number of bonding steps and so forth, right? So that's as big as 10x, okay, in terms of difference between a hybrid versus a TCB bonding, right? Cost of ownership running it, right? So if you think about running it running equipments on plasma and activations and clean and everything and CMP, it is going to cost a lot more than TCB. I don't have the number here, but our customers are telling us it's a lot more. And the third point I want to make is in OSAT environment, when they have no control of the dilets or the chiplets coming in, okay, the process of hybrid bonding makes it very complex, and the cost of complexities and process development is far greater than trying to do a TCB, evolution or scaling it up. All right, so I don't have numbers, but I can tell you that there are a lot of concerns raised, and this is why the adoption of hybrid takes a little longer than the TCB. And the second thing is what we've seen the success of hybrid bonding is mostly fab foundries assembly in one place, okay, controlled by the fab process and the assembly process versus OSATs, all right? And OSATs are taking a little wait and see approach because they want to continue to push the TCB further and further down the nodes. All right, so Subbu, you want to take the other question?
Yeah, and let me add to what Chanping said. The other very important thing to note is, nobody has today done hybrid bonding with dies that come from different foundries. So nobody's been able to show that, okay, I can put a global foundry die on a TSMC substrate or whatever it is. Nobody has done that. But with thermal compression bonding, we do that all the time because we're beggars, so we'll take dice from anybody who gives it to us free, So that it does work. So in terms of the second question had to do with conductivity, and I'll answer both thermal conductivity and electrical conductivity. Okay, the copper to copper bond is basically a native bond, right? It's like welding two copper pieces together, and so the thermal conductivity is across that interface. Okay, is the interface disappears pretty much because the grains interpenetrate, and so the thermal conductivity and the electrical conductivity are comparable to what you would get in bulk copper. Okay, and so you won't see any discernible difference in either of those two parameters. Now, the question that somebody might ask is, but far away from the bond interface, you may have some Kirkendall voids. Okay, those Kirkendall voids will exist in no matter where you do it, because the diffusivity of copper across that interface, okay, is going to be one is going to diffuse faster than the other because of the metals come from different sources. Okay, they will have slightly different texture and slightly different microstructure, and therefore the diffusivity, actually the grain boundaries are different density. So you'll have different kind of diffusion from one to the other. One will go faster in one direction, the other will go slower in the other direction, and so you leave a void, right? Now, what is the fraction of those voids? The fraction of those voids is negligible compared to the overall density of the copper. And so they may be a 10 to the minus 2%, okay, of difference in the conductivities because of those voids. So basically, my net result is that there is no impact, and you can assume that these are like I would say 1,000 times better than solder joints.
Great.
Okay.
Thank you very much, Subbu. Yeah, Chanping, did you want to add to that?
Yeah, no. I just want to say maybe we can take one more question before we wrap up. I know we are at the top of the hour already. All right, so
yes,
maybe
exactly. So
yeah.
I'll combine two of them here, and these were related, I think, to the process where you have the pre-applied underfill. So there was a question regarding any concerns about the CTE mismatch of that underfill material and the copper, and then do we care if the intermetallics are brittle, if they're supported or contained by the underfill?
Subbu, you want to take that?
Yeah, so yes. So I think, generally speaking, I think if you're talking at one of the reasons why we haven't been able to actually shrink the pitch of solder-based copper is actually because of these intermetallics, all right? And the brittleness of the intermetallic is not something we can just sort of ignore. It is a factor. And the reason why we put underfill in solder joints is because of this problem. And the adhesion or the two die or the die or the substrate is actually held by the underfill. Most often, right, this underfill is an organic material. And so if you have an organic material sandwiched between two silicon pieces of bread, so to speak, okay, you are definitely going to have thermal expansion issues. And so you have to be able to accommodate that, and you have to make sure that your underfill is strong enough to withstand that and take that sort of thing. So so this is what limits the scaling. And I think people have been trying very hard. I mean, Intel in their Ponte Vecchio sort of product pushed this to about 36 microns. And I remember a talk that somebody gave from Intel saying, look, we are unable to get you the dimensions below 36 microns, and primarily because of all these issues. So, our approach at UCLA and for the fine pitch TCB has been, let's eliminate the organic material. Okay. And if you just keep everything silicon, copper, and oxide, okay, this becomes very, very similar to what we have on a silicon monolithic die. Okay. And so the challenges of that have been solved. Okay. And I don't think there's an issue. And so, yes, so I think to net it out, yes, as you go to finer dimensions, solder intermetacks are an issue, and two, underfill doesn't work as well. And therefore, eliminating them is actually the goal of our program.
Great. Thank you both very much again for your time and sharing the evolution of this work. I think very interesting and very timely, as Chanpin pointed out in the earlier part of the presentation today. So, and thank you to everyone who joined us today. As Surya-san mentioned, we will send out a link to the recording and presentations for you to download. And we really appreciate your time and hope you'll join us again on one of the future webinars in the packaging series. We also run them in smart manufacturing and sustainability presently at the moment. But the next packaging one is on October 28th. And hopefully we'll have as good an interactive crowd again for that one on the 28th. Thank you all very much, and thank you in particular to Subbu and Chanpin for their time and effort.